Hi everybody. In this video we're going to find the interval of convergence for each of the following series. Alright, so to find the interval of convergence we first have to find the radius of convergence. And to find the radius of convergence we need to apply the ratio test. Alright, let's do a little cleanup and then we'll find the limit. Okay, remember x to the n will cancel with x to the n, just leaving x to the first on top. We can't divide out the n with this n right here, so we'll just bring those over. We have x times n on top and n plus 1 in the denominator. And remember, this is a limit in terms of n, so what we can do is we can bring out the absolute value of x. Leaving us to find this limit. And then evaluating this limit right here. When you plug in infinity, you get indeterminate. Remember, you can apply L'Hopital's rule, and we're going to get 1 over 1. So this limit goes to 1. So we have the absolute value of x times 1, which is just the absolute value of x. Remember, we're in the ratio test, and if we want this power series to converge, we need to make sure that using the ratio test that the absolute value of x is less than 1. Alright, so coming down here and documenting what we have the radius of convergence of 1. Okay, and then so far our interval of convergence would be to stay within 1 unit of the center. And remember that the center of this power series is x equals 0. So if your center is x equals 0 and we have to stay within 1 unit of x equals 0, we can go to the left to -1 and to the right of x equals 0 to +1. So far our interval of convergence is going to go from -1 to 1, 0 being the center. Alright, at this point we need to check the endpoints to see if we should be able to include those, if those are good x values that makes this power series converge. So we're going to test endpoints. So just a note to self. Alright, so what does that look like? Well, we're going to start with x equals 1. So come down here and say, alright, we're going to let x equals -1 in our power series. Alright, so going back up to the power series and replacing x with -1, we end up with this series of constants. So if x is -1, I've got -1 raised to the nth power. Thinking about that, we're going to have an alternating series. Alright, and then back from our background, using all our different tests for convergence and divergence. Alright, we're going to use the alternating series test. So just a note to yourself what you're doing. Alright, there's 2 parts to that test for convergence. And remember, alternating series test is a test only for convergence. Alright, part 1 has us looking at the limit of the nth term. So the limit as n goes to infinity, and we disregard the alternating sign, so we just look at it as 1 over n. Alright, and finding that limit, we get 0. So far, the AST test is working. The first condition is met. Alright, and the second part of the alternating series test says that we need to compare consecutive terms. So I'm going to look at the term of a sub n plus 1. So that means everywhere I see n, I'm going to replace it with n plus 1. So that term would be 1 over n plus 1. All right, and then we want to make certain that that term, the one that follows the previous term, is always smaller, that the terms are getting smaller. All right, and the term before it would just be 1 over n, and we would call that, if we wanted to give it a name, the a sub n term. All right, and so for values of n, we can see that this term will always be smaller than this term right here. All right, so both conditions are met for the alternating series tests. Okay, so that means that since it does converge, that we do want to include the negative 1 here with a bracket. So we'll make that adjustment in a minute. All right, let's test the right endpoint. So we let x be 1. Go back to the original power series. Everywhere you see x, replace it with 1. So 1 to the n just becomes 1. The denominator is n. Okay, and we already know what this is. This is a divergent p series. The special case that it's the harmonic series when the exponent is 1 right here. So I'm just going to put a note to myself that this diverges. Diverges by the p series. So what that means is that we can't include the x equals 1. All right, so making the adjustment here, recording the interval of convergence. Maybe I'll come back up here and say that the interval of convergence is including negative 1 up to 1. So, and another way to think about that is that any x value that falls in this interval, including negative 1, excluding 1, any of those x values, when you replace it in for this x in the original power series, right up here, that this becomes a series of constants, and that any of those series would converge as long as you replace it with any of these numbers here. A graphical approach is if you were to expand this series and graph each of the terms in a y1, y2, etc., picking up an additional term, that you can see that this this series is going to grow and lay on top of each other, no matter how many terms you add, only on the interval from negative 1 to 1. Right, so this is our answer right here. Whoop. You get the idea. All right, let's find the interval of convergence on our next example. All right, so to find the interval of convergence, we must first find the radius of convergence, which means we have to apply the ratio test. So I'm going to get that set up here, and I'll join you in just a second. All right, hoping that you have this same setup here, let's begin the simplification process. All right, since we're finding the absolute value, we can go ahead and cancel here and here, because that results in a positive anyway when you find the absolute value. All right, I can see that quantity x plus 1 to the n will cancel with this quantity x plus 1 to the n, leaving just quantity x plus 1 to the first. Okay, and canceling across here, 2 to the n is going to cancel with 2 to the n here, leaving 2 to the first. So the cleanup over here results in us having just x plus 1 in the numerator. Looks like the denominator just has 2. All right, this is a limit in terms of n, so I can go ahead and pull out the absolute value of x plus 1 from the numerator. Leaving me to evaluate the limit as n goes to infinity of 1/2. Well, we know that that limit is just going to be 1/2. So what we end up with is the absolute value of x plus 1 all over 2. Think of that as 1/2. And that's our answer for all of this right here. Okay, well, using the ratio test, we want this to converge, so we want this to be a number less than 1, so we force it to be less than 1. All right, and to continue, I want to isolate the absolute value of x plus 1, which represents the center of my power series. So I'm going to multiply both sides by positive 2. Okay, and in doing so, multiplying by a positive number doesn't reverse your inequality symbol. So I get this expression right here. So this tells us that the radius of convergence is 2. I need to stay within 2 units of my center. All right, so at this point then, before I do any testing of endpoints, I have an interval of x's, okay, that would make this series, this power series, when converted to a constant, a series of constants, converge. All right, so again, my radius of convergence is 2. I need to stay within 2 units of my center. Remember, your center is x equals negative 1. So if you need to use a number line to help you, fine. If my center is negative 1, right here, this is my center, I have to be within 2 units to the left and 2 units to the right to make the power series converge. So that would put me at negative 3, and it would put me at positive 1. So my interval of convergence is negative 3 to positive 1. All right, so now we need to test endpoints to see if we can include either one of those x values. So we come down here, and I'll just start with letting x equal negative 3 and see what happens. That's negative 3, sorry. So go back to the original power series, and wherever you see x, replace it with negative 3 so that it becomes a series of constants, and I can apply all my different tests for convergence or divergence. All right, so back up here. Okay, negative 1 to the n. It looks like it's going to be the AST test. Plug in negative 3 here, you're going to get negative 2 to the n, all over 2 to the n. All right, I want to do a little more cleanup here to help me with my work. Okay. All right, that cleanup would have us look at the numerator. We can do something with that. I'm going to work to the side a little bit here, so I seem to have some room. Okay, mathematically, you might see that the product of this numerator is going to actually just reduce to 2 to the n. The math on that is this. All the legal math that can be done right here. Okay, I can think of that as negative 1 times positive 2 inside raised to the n power. Now I'm going to come down here. Okay. I'm going to take all these steps on this problem, but if we see this in the future, we can just go right to the final observation. Okay, now right here, okay, properties of exponents back from Algebra 1 allow us to do what I'm about to do next, which means I can take negative 1 and raise it to the nth power, and I can take the positive 2 and raise it to the nth power. And I still have 2 to the n down here. Okay, and as a final cleanup, notice what happens in the numerator. Okay, I still have 2 to the n up here, but the product of these two would result in us having negative 1 raised to the 2n power. Well, if you think about combining this and that being negative 1 to the 2n power, no matter what number you put in for n, whether it's odd or even, okay, that product is always going to be an even number. So negative 1 to an even power is going to be positive 1. So this really is just equal to 2 to the n over 2 to the n. Okay, well, you can cancel those, and that's just 1 right there. So this term really just simplifies to 1. So that just means if we were to expand this series of constants, we're going to get 1 plus 1 plus 1 plus 1. Well, find the limit of the nth term. The limit of 1 is 1, which is not 0. And by the nth term test for divergence, okay, this series diverges. So that tells us we would not want to include negative 3, so we would leave this as a parentheses and not a bracket. All right, so at this point right here, I might just put a note to myself and just say diverges by the nth term test. Remember, that's just a test for divergence, not convergence. All right, we still need to test the right endpoint, so let's let x equal positive 1. Go back to the original series. Wherever you see x, replace it with 1. Okay, when x is 1, we have 2 to the n here, and we still have 2 to the n here. All right, well, we can quickly cancel these two right here. So when these cancel, we just have this term. All right, if you were to expand this, you're going to see that you're going to have 1 minus 1 plus 1 minus 1, etc. That's not going to converge. That's actually going to diverge, so I might put a note to myself. This diverges also by the nth term test. Even though it's an alternating series, we can still find the limit of the nth term. And it's either going to be 1 or it's going to be negative 1 or negative 1. It alternates. And neither one of those numbers, 1 or negative 1, is equal to 0. So diverges by the nth term test. So the left endpoint and the right endpoint diverge by the nth term test. So I might just come back up here and just say my interval of convergence is -3 to 1. Okay, another way to double check that is you could expand this power series and graphically approach term by term, or I should say, graphically approach the first term, graphically approach it by graphing the first term, graphing the first 2 terms, the first 3 terms, the first 4 terms, and seeing that they overlay on each other or grow as long as you stay within -3 to 1, within 2 units of the center. All right, let's take a look at our third example here. Let's find its interval of convergence by finding the radius of convergence, which means finding using the ratio test. All right, it'd probably be good to notice what the center is first of all. The center is x equals 0. All right, and then we have quantity n plus 1 squared. That setup's not too bad. All right, let's see if we can do some cleanup. Right, x to the n will cancel with x to the n, leaving x to the first on top. We could not reach across and cancel this n squared with that n squared there. We could expand this denominator if we wanted to. I don't think it's necessary. I think we can see what's going to happen in a minute. So in the numerator I still have an x times n squared. That's a times. And then I could expand this and get a trinomial. It'd be n squared plus 2n plus 1. Again, like I said, I don't think it's necessary. This is a limit in terms of n, so let's pull out the absolute value of x. Okay, and then to evaluate this limit right here, you could expand the denominator if you wanted to, but just think about what your highest term is going to be anyway. It's going to be n squared plus a 2n plus 1, but your leading term will be n squared. If you plug in infinity right now, you're going to get indeterminate, which means L'Hopital's rule. But eventually what you should see is that when you do expand this and you have the leading term of n squared, we'll go ahead and expand the whole thing, that you might remember from your past that these coefficients right here would be made into a fraction. You're finding the ratio of the coefficients. So actually this whole limit right here is the ratio of these coefficients, or that whole limit equals 1. Alright, so we're at the point where we have the absolute value of x, and this whole limit goes to 1. So we just end up with the absolute value of x. Okay, and if we want this power series to converge by using the ratio test, we must force it to be less than 1. Alright, this is isolated as far as x is concerned here. I don't have to do any kind of math to it. like I did in the previous example. So what that means is our radius of convergence is 1. And currently, until we test the endpoints, the interval of convergence would be to stay within 1 unit of the center. And again, the center is x equals 0. So 1 unit to the left puts us at -1, 1 unit to the right puts us at +1. All right, and let's test the endpoints. Alright, I'm going to test the left endpoint first, so let's let x equal -1 in the original series. So that power series becomes a series of constants. If x is -1, we have -1 to the n over n squared. So this looks like an alternating series, so we would apply the alternating series test here. The first condition is, let's look at the limit of the nth term. Right, so we're looking at 1 over n squared. Yes, that does equal 0, so we can continue with the AST test. So let's look at the term a sub n plus 1, which would be to take n and replace it with n plus 1. Okay, and is that term always going to be less than the one before it, which is just 1 over n squared, which we would call a sub n. And yes, this term would always be smaller than this term because this denominator is bigger, and if it's a bigger denominator, then we know the value of that fraction would be smaller. So yes, I put a check there, converges by AST. So I am going to want to put a bracket around the left endpoint. And let's check our right endpoint. Let's let x equal 1. So back to the original power series, wherever we see x, replace it with 1. Well, 1 to the n is just 1 over n squared. And that's a convergent series by p series. So I would just put a note to myself, converges by p series. Where p is greater than 1. Alright, so back up here then, our interval of convergence must include both endpoints. So we'd have a bracket on both. So I tried to share with you different examples with what happens at the endpoints and the different situations that may apply. Sometimes you include both endpoints, sometimes you don't, sometimes it's just one or the other endpoints. But overall, just the idea of finding the interval of convergence puts us back to finding the radius of convergence, which again just means using the ratio test to get us started.